Hi, I'm Emil Grønbæk from Aarhus University in Denmark. This research is done in collaboration with co-authors from Aarhus, Majken, Kim and Marianne, and is supported by Microsoft Research and the KV Lab. The talk is about KirigamiTable, a shape-changing interactive tabletop designed to support transitions between individual and teamwork. The core motivation of this research is designing for transitions in collaborative work. In a previous paper, we coined the term Proxemic Transitions to articulate the dynamic interplay between people, computers, and physical environments. In a field study, we found that during transitions, people often adapt to the environment for co-located collaboration. Imagine if we could instead physically reconfigure the computing environment. This is one of the great potentials of shape-changing interfaces at the scale of furniture. Researchers such as Takashima and colleagues and Ishii and colleagues have contributed prototype concepts of both shape-changing tabletops and wall displays. These are all focused on supporting transitions in collaborative work. But most of this prior research has focused on triggering shape changes and not so much on the actual interface transitions. In order to explore this gap, we developed KirigamiTable. With KirigamiTable, we make the following contributions. A novel user interface that supports collaboration around shape-changing tabletops, a set of interaction techniques that combine shape and content transformations, and demonstration of the principle of Kirigami actuation for tabletops. I'll structure this talk by going through each of these contributions. First, let me show you a clip of the possible shape changes with KirigamiTable. Our first contribution is the design of the user interface for KirigamiTable. As you saw in the video, the table supports 3 configurations: flat-fold, 4-fold, and 2-fold. And the user interface is designed to exploit the qualities of these configurations for transitions in collaborative work. I'll first briefly explain how the prototype is implemented. For the display, we use dynamic projection mapping, where the current state from the actuators is used as input to adapt the graphics in real time. And an important disclaimer, all the interactions you will see are simulated via Wizard of Oz. I'll now talk about what we developed for the user interface. We see a great potential for KirigamiTable in supporting the social dynamics of creative work. To inform the interaction design, we developed an application scenario. The scenario is based on analysis of creative collaborative practices, and we found that they often involve transitions in the physical configuration of people. We have focused on one example, inspiration card workshops. It is a collaborative workshop format where technology experts and domain experts co-develop design concepts together. KirigamiTable is well suited for this use case. The workshop has a well-defined structure that takes participants through transitions between different physical configurations, working in sub-teams, individually, and as a whole team. I'll now play a video of the use case with KirigamiTable. So, for shape-changing tabletops, it is not just the contents that are dynamic, but also the shape of the interface. And this requires that we completely rethink the interaction design. I'll now explain some of our interaction techniques, and these techniques are based on our work of addressing core challenges identified in prior work, and it is important to mention also that these are just a first exploration, so you should only regard them as design proposals. For this talk, I will focus on a few examples from the paper. First, I'll show how we have explored different ways of initiating transformations. We demonstrate two different approaches that both combine content and shape transformation. The Shape First widget has the three possible shape configurations as top menu items: flat fold, four-fold, and two-fold, and for each one the user can then select between meaningful options for the content. The Content First widget supports the reverse interaction starting from the content items. A key difference in the two techniques is that the Shape First widget is permanently visible, whereas the Content First widget appears in context after a user has selected a group of items. Now, another important question is, what happens to display contents during and after shape transformations? I will here focus on one example from our techniques that aim to address this question. What you've seen in the videos is that we propose to utilize shape changes for applying actions on the contents, such as subdividing, duplicating, or sharing items. But how can users anticipate shape changes to affect the content? We suggest a feed-forward mechanism inspired by Lindelbauer and colleagues, where we virtually alter the appearance of the Kirigami surface to preview how content will be reorganized. Specifically, we highlight edges on the surface folds and animate them to indicate zones for how contents are reorganized. You saw a glimpse of it earlier, but here it is in a bit more detail. Finally, I will talk about the principle of Kirigami actuation. The principle comes out of mechanical engineering research. Diaz and colleagues coined the term to refer to the design of mechanical actuators, where folding and cutting principles are used to generate different kinds of linear actuation, like rotations and lifts. So far, the experiments have been at the scale of paper sheets, so KirigamiTable is an experiment in scaling up the principle to furniture scale. We did several experiments on the table surface regarding size, dimensions, and different materials, as seen in the photos. And we are currently using a foam board, but want to build a more robust construction for the future. The undercarriage for the table construction has been built and generously provided by the Danish company Linak. It consists of 4 linear actuators, 2 vertical actuators for height shifting, and 2 horizontal actuators for deforming the Kirigami surface. The 2 horizontal actuators expand in opposite direction, enabling a centralized surface deformation. This is a relatively simple construction if you compare to related systems. Often much more complex setups are needed for surface actuation. But in our approach, it is the Kirigami patterns that do the heavy lifting. We use only simple linear actuation to achieve complex deformations. To conclude the talk, with KirigamiTable, we have contributed a novel interface for collaboration, a set of interaction techniques, and a demonstration of Kirigami actuation for tabletops. Thanks for listening.